Hello again. This is Roger Koch Barr, the instructor for bioelectricity, and we're in week 2, and this is the 10th lecture. The question for this lecture is, why is Cm, the membrane capacitance, so big, way bigger than you would normally expect? And the answer, very briefly, is because the membrane is so thin. In biological membrane, the membrane capacitance is about 1 microfarad for each square centimeter. Now there is a lot of centimeters squared of membrane surface in just one person. So if you were to say that in a person there's 1,000,000 centimeters squared, that would say the total capacitance within a person would be 1 farad. When I was in school, I remember a teacher telling me that 1 farad is so much capacitance that you could not imagine it existing in the whole entire world. Well, he meant that as a good illustration, but he was not thinking in terms of bioelectricity. If you think in terms of bioelectricity, each of us may carry around a whole farad of capacitance, which is an enormous amount. To think about why Cm is so big, you have to think about, why is the membrane so thin? Let's just think about the following experiment. We would say for flat plates, capacitance can be found by the formula C equals epsilon 0 A over D, where epsilon 0, or epsilon, is a constant that has to do with the material. The material can be air, the material can be membrane, and epsilon changes accordingly, according to what the material is, but it has a value that's more or less known. The point of looking at the equation is to see that the capacitance gets bigger when the area gets bigger, and it also gets bigger when D gets smaller. So a bigger capacitance occurs with a bigger A or smaller D. So you might, if you draw this out, you might say, okay, here's our capacitance, here's the outside, here's the inside, D is this thickness, A is the area. Surface area. Now let's do a little comparison with an ordinary object. Think about a stack of 1,000 sheets of office paper. You can do this experiment yourself. Get 2 reams of ordinary office paper, like copier paper. Stack one ream on the other. You know, ream is a package that has 500 sheets. So get 2 packages of office paper, like copier paper, put them on top of each other, and then measure how high the stack is. I did that. I actually did it in preparation for this lecture, and my stack was about 4 centimeters high. That means that the thickness of 1 sheet of office paper can be found by going through this calculation, 4 centimeters for 1,000 sheets. And I think that results in about 400,000 angstroms for 1 sheet. 400,000 angstroms for 1 sheet. So if now we compare the thickness of paper to the thickness of membrane, we'd say, well, these things are quite different thickness, because with paper it is 400,000 angstroms. That's just a numeric conversion from 4 centimeters into angstroms. 1 angstrom is 10 to the minus 10th meters. About 40 angstroms thickness for membrane. That is to say, the thickness of the non-conducting region is about 40 angstroms. So the ratio there is 10,000. Wow! Take a piece of office paper, hold it up in front of you, look at it on the edge. Now when I do that, my vision is not perfect, so I barely see anything when I hold it and look right at along the edge to see the thickness of a single sheet of paper. Nonetheless, it is 10,000 times the thickness of membrane. Well, whether or not we've done the calculation exactly right, you get the point. It's thousands of times thicker to have a sheet of office paper than it is to have a sheet of membrane. So since the capacitance goes inversely as to thickness, the thinner the membrane, the greater the capacitance, and the conclusion is membranes have a lot of capacitance. I don't bring that up just as a random thought. The fact they have a lot of capacitance means that they can store a lot of charge, and that's very important to their electrical function. Another fascinating item is that all electrically active membranes, from whatever organ or system within you or people or animals or other electrically active structures, they all seem to be built out of the same kind of lipid bilayer, more or less. And the corollary of that is all electrically active membranes from whatever organ or system have about the same amount of capacitance. So you read different problems or different situations, and in those you have to specify a lot of different parameters. Oftentimes the membrane capacitance is one of them. You can almost think of it as a constant of nature, maybe not quite like pi or some other mathematical constant, but you can just be sure it's going to come out to be around about 1 microfarad per centimeter square, not too far from that. So thank you very much for your attention, and in the next segment we'll move on to a problem session.